Good afternoon. So I'll be going over the new hydrogen supplement that will be released by the end of this year. That's going to be a part of CSA Z341. And we'll talk about a few topics in there. I'll also get into hydrogen properties and where the industry is currently at. In 2014, Toyota released the first hydrogen fuel cell vehicle, which is interesting that they sold about 20,000 units worldwide. And of course, the issue being, where do you fuel it? But anyway, the technology is there, and then, you've got some concept, transport cargo ships and supercars. If you're not familiar with Z341, that is the storage of hydrocarbons in underground formations. Originally published in 1993, the sixth edition has come out in 2022, and there's a new release every 4 years. There's three components of it currently: reservoir storage, salt cavern storage, and salt cavern waste disposal. And that image there is some of the work we do on cavern mapping, and that's in a salt dome. The white mesh is a outline of the salt dome, and all the caverns are on the inside. For context, these are domal salt caverns. They're many thousands of feet tall and 200 to 300 feet in diameter. So typically on the order of millions of barrels of storage space per cavern. What is CSA Z341 used for? Minimum requirements for the design, operation, maintenance, and abandonment of underground storage systems. It's not supposed to be a design handbook, and it is subsurface focused, but it includes the wellhead and the first ESV, outside that wing valve. The problem here currently is that it's not applicable to compressed air, hydrogen, ammonia, noble gases, or bionuclear waste. So Z341 is maintained by a volunteer technical committee. It's composed of operators, regulators, and consultants. I've been on the committee for 8 years now, and I'm a vice chair on the storage side. Like I said, a new edition is released every 4 years, so the next edition will be 2026. The updates that are made reflect, industry technology changes, better clarification on certain requirements. The problem is that actually in the next 2 to 3 years, operators are trying to develop hydrogen storage facilities in Canada. Waiting for 2026 to release a hydrogen storage minimum requirement wasn't fast enough. And so a subcommittee task force that I was on was established to develop the hydrogen supplement, and then that was presented to the larger committee. And the larger committee is composed of about 40 people. So getting into the hydrogen supplement, the standard itself is very comprehensive. To really dig into it and to understand underground storage principles, it would take multiple days, I'd say a week, to really dig in and go through it. I'm just going to hit on some high points here about the hydrogen supplement. So some of the main changes that were made, applicability of the supplement. So the standard still has precedence, and the supplement is to be used concurrently with it. So anywhere the supplement says there's a change for hydrogen storage asset, you have to follow the supplement. If there's no change, then you revert back to what the standard says. It's applicable to greenfield, new construction sites, and conversions or brownfield sites. Still, it excludes ammonia, methanol, and in situ hydrogen production. Those pictures on the right, the bottom one's actually a cavern in Sarnia, bedded salt, and then the top picture's a cavern in western Saskatchewan, bedded salt. Okay, first topic related to geological and core testing. One of the main things is that we wanted to ensure that the cap rock, the sealing formation above the salt or above the porous reservoir, can hold hydrogen or not let it seep through. And so we're requiring permeability testing with hydrogen on the cap rock core and storage formation core. And then also compatibility testing with native formation fluids and mineralogy. And these are some images of salt core. It's 4-inch diameter core. The one on the left is showing how salt creeps and deforms when pressure is applied to it over time. And so that's literally the change when steady state pressure is applied to salt. The middle picture is a core of bedded salt, and just shows that there's insolubles, non-salts in the salt. Nice clean halite crystals at the top half there, and then getting into, an anhydrite stringer or sandstone stringer below. And the picture on the right is just of salt crystals in a core. So breaking open a core and actually looking at the salt crystals, just like in your table salt, you sprinkle it out and those are individual crystals. Subsurface is the same thing. Some salt formations have crystals that are 2 inches in diameter. The pressure downhole and the temperature is what essentially fuses the crystals together, but at the same time allows them to move and absorb stresses. On the material side, one of the big concerns is hydrogen embrittlement and the cracking associated with that. In simple terms, at an atomic level, the hydrogen will permeate the steel, and it is stored there, until the pressure conditions in the system change. And the hydrogen existing there then affects the performance properties of the steel and the casing. And so you have to have the right metallurgy to withstand those conditions. And it also, you have to consider the impact of hydrogen on seals, rubbers, gaskets, other types of lubricants and greases that might be used. Dual barrier philosophy. So in the industry, the oil and gas industry and the storage industry, this isn't a new philosophy. It's been around, but for Z341, and Canadian storage in general, I'd say it's newer, or definitely a newer minimum requirement. The idea is that from your storage zone up, including the surface, you'd have 2 barriers between your hydrogen product and the environment. If it's the formation, outside the storage zone, or, the atmosphere. There's a lot of different configurations that could achieve a dual barrier system, and that's just an image of one of them, the blue being the primary, the first barrier, and the red being the secondary barrier. And so that includes the casing and the wellhead components. Another thing on the casing design, the primary barrier has to be either welded connections or hydrogen leak tight tested connections. And so there's a few on the market these days that have the testing proven in a lab to be hydrogen leak tight tested connections. They're premium connections. Valoric is one of the companies that makes that type of connection. Cementing, that's another consideration, how hydrogen's going to affect the cement performance and permeability. Casing inspection logging, now that there's the dual barrier design system in place, we wanted a 10-year inspection, which the frequency is no different than the regular standard, but we wanted a direct casing inspection of the primary barrier and a through tubing indirect inspection of the secondary barrier. And then well servicing, just to be mindful of hydrogen impacting certain things, well control equipment and such. That's one of our operations down in South Texas in 2019. That was the largest onshore snubbing operation. We had to build a custom snubbing stack to do that. That was on a gas cavern, snubbing 10 3/4-inch casing. MITs, high level. The gold standard is the nitrogen brine interface MIT for the industry. The idea is that you've got nitrogen represented in yellow that's injected down the annulus, and you establish it below the cemented casing shoe. You monitor that interface, you monitor temperature and pressure, and you do mass balance calculations to determine if you've lost nitrogen. And so what you're testing here is the seal at the casing shoe, the cemented casing integrity, and the wellhead integrity. And then the cavern's full of brine, or it could be full of product, and it's pressurized up to the maximum allowable pressure. So in short, there's an acceptable leak rate. So when you're calculating the nitrogen volumes, there's there's some error. And so the acceptable leak rate is sort of what represents the error, also known here as the calculated nitrogen leak rate. And so for typical nitrogen tests in Canada, what's allowed is that you can have a CNLR of under 160 cubic meters a year. That's 1,000 barrels a year. For hydrogen systems, if you test with hydrogen, then you can have the same criteria under 160. If you test with nitrogen, because hydrogen has a higher propensity to leak due to dynamic viscosity and other properties, we've reduced that minimum requirement to 60. Hydrogen properties and some industry news. So Canada has a hydrogen strategy. At the end of 2020, the government of Canada released this strategy. You can read it online. Essentially, it's to support GHG emission reduction targets, and hydrogen can be blended with natural gas to reduce greenhouse gas emissions. So there's a lot of municipalities and operators considering that. And there's interplay with CO2 sequestration. So, the hydrogen industry really, you'll see, is more of a supplement to the overall kind of energy industry and GHG reduction targets. The colors of hydrogen. It's not standardized yet. I'm sure at some point it will be. But the interesting thing here is that 95% of the world's hydrogen production currently is from processing hydrocarbons. So your gray and your brown hydrogen, either through steam methane reforming or gasification of coal. You can turn that into blue hydrogen and sound nicer, right? By capturing the CO2 produced in that process and then storing it. And then you've got green hydrogen, which is from water electrolysis. And then there's some other colors that I added there. I found them on Google. Didn't even know pink and yellow existed, but somebody made them up. So there you go. Hydrogen energy system. I think you can kind of envision it. Essentially, you need electricity to produce the hydrogen in some form. And so you can get your electricity from a number of sources. The hydrogen is then used for a number of things. It's currently used throughout industrial processes, metals refining, creation of ammonia, which is then used for fertilizer, et cetera, et cetera. Transportation, that might become a bigger component of where hydrogen is used in the near future. And then you circle back, you can even use hydrogen for power generation or to supplement it and create electricity. There's a number of hydrogen storage facilities in service today. There's 3 facilities, domal salt facilities down in Texas. There's a new project out in Utah, and then there's a cavern facility in UK as well. And actually there's some hydrogen reservoir storage, aquifer storage in Europe as well. The buzz that we're involved in and been hearing is Alberta, Nova Scotia, Ontario, South Texas, South Louisiana, North Dakota, actually. Those are more active projects that will most likely be constructed in the next year to 3 years. And then we've been doing a number of feasibility studies across North America just for companies to learn how they could potentially, build a hydrogen facility. Okay, some properties. I'll cruise through this because the end goal is to understand where hydrogen fits in on the energy density scale with other energy sources. So hydrogen is far less dense than, say, methane. And so to get the same mass of hydrogen in the same geometric space, it takes a much greater pressure to compress it. Here's a couple other examples. On the bottom of these graphs, you can see you've got methane, butane, propane, ammonia, air, and then the green line is hydrogen. So as temperature rises, it affects the volume, the geometric space that hydrogen will take up much more than the other fluids. And same with pressure. That just illustrates that it takes considerably more pressure to compress the hydrogen into the same volumetric space as the other fluids. Density. As you increase the pressure, hydrogen density doesn't change that much, whereas for methane and air it does. or it does more so. And so that's just a comparison between the mass of hydrogen versus methane in air in the same size of cavern. So, considerable difference. And that leads you to energy density. So hydrogen down at the far right there, that's gas form. To liquefy hydrogen, it has to be extremely cold, refrigerated. You've got ammonia, which is NH3, liquid natural gas, propane, butane. So there's a huge gap between gas phase hydrogen and commonly used, natural gas, propane, butane fuels. So possibly a way to overcome that, at least in part, is we'll probably start hearing more about ammonia storage and ammonia transport. Hydrogen might be what's actually used ultimately in the vehicle or the ship or what have you. But ammonia is a much more efficient way to transport it and store it. So there's benefits to that, but there's also storage complexities, significant storage complexities. So we'll have to work those out. And this is a little bit about me and the suite of Lonquist companies. And yeah, that's all I got.